video, I will solve the shallow truss problem without actually modeling the stabilizing spring. The, the method that I'll be using is called displacement control though. This video is prepared for the 3D Experience 2022X version. Okay, now uh, the purpose of these videos is for people who want to use the native solver of the 3D Experience platform to solve some classical problems. Okay, such problems are done with other software and they can be found on YouTube or other internet resources. Now, the problem that we want to do is this a truss problem, a two-dimensional truss problem which is pinned at the two ends, and there is a load P, 2P acting on the top. Now, because of symmetry, we need to model only half of this, and here the length of the member is L, and this thing, this offset is Z. Shallow truss means that Z is much smaller than L. Okay. Now, I want to remind you that I've already done a video segment on this where I actually solved this problem by, uh, by putting a spring here, okay? Uh, the reason is that without any additional work, additional spring, basically the load deflection of this curve looks like that. As you start increasing the load, this thing goes down, but reaches a point where either the software crashes or in reality what happens, the reason that happens is that at this point stability is lost, and that's why the software doesn't complete the job. Okay. Now, uh, if you put a spring here, as I did in my earlier video, uh, that will solve the problem. You can still solve this problem with additional spring. However, if the stiffness of that spring is progressively reduced, so that in the limit basically the stiffness becomes zero and there is no spring anymore, then beyond a certain point, a stiffness value, same issue will prevail. Okay. Now, this approach of applying the load, specifying the load, and basically asking for displacement is called load control. Okay. The way I'm going to solve this problem without actually modeling the spring is will not specify the load level. I will specify a displacement, and you will see that if I do that, it will do the trick, and actually you can traverse this entire path, and this is called displacement control. Okay, there's some comments that I have at the end of this PowerPoint that I'll mention later on. Uh, the analytical solution of this can be found in these references. Now, when I have a spring modeled also, there is an additional term here, okay? But we're not going to do that. Therefore, this is our analytical solution. So whatever we do with the native FEA solver of 3D Experience is going to be compared against this value, okay? Now, the data that I take is from those two sources. These are the dimensions, length of the bar and the offset, area cross section, and the Young's modulus. Uh, and notice that when the displacement is 55 millimeter downward, the load is 13.2. So the end result is that I should match this, and that, of course, comes from this curve up there, from the formula up there. The force deflection curve for the case that you're trying to do looks like this. So at the end of the video on 3D Experience, I will actually generate this plot for you. Okay, this is obtained by plotting that analytical solution. So here are the comments that I'm going to ask myself is, well, first of all, we will see that the shallow truss problem cannot be solved with the load control. I just said it. Okay. and but it can be done with the displacement control. So the natural question is, well, why don't we solve everything with displacement control? In other words, using this trick. The problem is that not every problem enjoys this luxury. Okay, now there's under some restrictions, even if you have load control. Okay, like the shallow truss problem. Even if you have a load control uh, when applied to the shallow truss problem without a spring, it didn't work. But under some restrictions, okay, there is an approach called the Rick static step. It's not a general static step that I'm doing, which actually uses something called the arc length method, and it will work. So sometimes you cannot apply it as a displacement control problem, but you can do it as a load control because you know the load level, etc. You may not know the displacement level. Under certain assumptions, you can also do the load control. However, you have to use the Rick static step as opposed to general static step. I will do a video about this thing later on. Okay, let's go ahead and create this model. So I started with a part file, as you can see. So I will create 2 points and the line between them to represent the actual truss member. So 2 points. First one is 0, 0, 0. Okay, the next one is y of 2,499.875, and a height, that's the offset of 25 millimeter. Okay, yeah. All right, and then we're going to fit this thing so that we can see. Here's the fit. These are the 2 points that I created. So back to essentials and create a line point to point from here to there. Now, notice that 2 points were created. So what I suggest is strongly to hide these because when you try to apply loads and restraints and things like that, if you put it on the on the point, it's going to be part of the geometric model and not the finite element, and may not it will not work. And in fact, when you try to create a spring, if you were to do a spring, which I'm not doing in this particular problem, in this particular video, I'm not creating a spring, then one end of the spring cannot be that point. It should be the end, the vertex of that line. But in any event, I hit them. Okay, now let's go and create our material. So let's go to view and under, sorry, tools, let's go ahead and do a create a material. Let me give this thing the name shallow truss, no spring. Okay, make sure that the simulation is added. It is added there, and we say okay. Now notice that that model is created, that material model is created. Of course, there is nothing in it right now. It's blank, basically, file. We can apply it and then go and add the stuff later, or we can add the material now in this window and see now this one. Let's try it again. Somehow I got timed out. Cancel. See. Let me do that again. Shallow truss, no spring. I don't know what that timeout message was, but yep, simulation is there. So we say okay. right there. Right there. So right click. We can add the material properties right here actually. Let's do that. So this is Abacus multiphysics, mechanical, elasticity, elastic, and it is 500,000. So this is the 500,000. Yeah, the 500,000 e to the 6. Actually, we can say Newton per millimeter squared. And yep, it's good. We don't need the Poisson ratio because we are using beam bar elements. So good. So let me right click, apply. I don't need this. I go to my model, green check mark. And if we go and check it out, it will be the yeah, it will be the properties that I inputted. Should be right there. Very good. Save our model. That's pretty much it as far as the geometry is concerned. All right, so now we're going to go to structural model creation. We're going to use the empty FEM, blank finite element model, basically, no nodes and elements specified. Uh, so we go to mesh, use beam elements, although this eventually will be link, but anyway, right there. And I take a mesh size of 2500 millimeter. That means one element will be one element from left point to the right node. Okay, good. Now for properties, this is going to be a link element. So we go to properties. Under 1D here, we use link section. Now we select this line. Notice that as soon as we do, it takes the proper material and the area cross section is 100 millimeter squared. Okay, so the properties has been created there. Let me rename this also properties, and I'll call it shallow truss. Shallow truss, no springs, no springs, no stabilization spring. Say okay. All right, so that's pretty much it. In the other video segment that I did, the first one, I had to create a spring here, so I ended up going to connection, create the spring, but we don't need it here. Okay, first, what I'm going to do is I'm going to go to structural scenario creation, and I will do first apply a load, but then show you that the software will crash, not converge, and then we come and do it with a displacement constraint or displacement. What do you call it? Displacement control, right? Okay, so let's create our model, the model that we created right here. And now we're going to go and do static step right there. This one is the RIX, static RIX step, but yeah, this is a static step. Somehow in my PowerPoints, I said RIX static step. It should have been static RIX step, but that's okay. Here, that's not what we're doing now. Static step. Okay, so 1 second. This is a dummy time, so it doesn't matter what the total time is. However, because eventually I want to do a point displacement curve, so I'm going to make these increments smaller. So initial time increment and maximum time increment, so that I get more than one point and I can plot a curve. Okay, and here obviously the geometric nonlinearity is included. So large strain is going to be used if necessary. Okay, good. Now notice that these are both green check marks. That's because we have done the appropriate steps. Now we go to restraints. This end, not the point, this end, remember I hit the point, is going to be restrained in all three directions, X, Y, Z for translation. There is no rotational degrees of freedom because we're using a truss element or a link element. And this one, oops, see, inadvertently I selected the actual edge. So let me remove this. Let me go ahead and try to, there, that point, that vertex, not the point, the vertex. Does not move in X, does not move in Y, but it's free to move in the Z direction. Good. Let me put a load here. Let me put a load, and I will show you that when you apply a load, the software will not actually run. Okay? Now the load that I'm going to put in there, actually, it really doesn't matter what value you use, but I want 50, the 13, for example, 13.2 minus 13.2. Now notice that at 55 millimeters, when you apply a load of 13.2 Newton to this part, the truss, the middle node of the truss, this node will go down by 55 millimeter. Okay, so I'm using this expression. So when you apply displacement of 55 millimeter downwards from 155, the loads that's needs at 13.2. So I am going to apply 13.2. I better get a displacement of 55. You will see that actually it will not run. Okay, it will crash. Okay, so 13.2. Let's go back here and we go to load. We go to force. On this point, we apply a downward load of minus 13.2. Okay, there we are. Let's save our model and run it, and you will see that it actually will not converge. It terminates during the run. Okay, so let's go to simulate. Now also remember, I have to come back later on because I'm not going to be applying load, I'm going to be applying displacement later on. I will have to come back and ask for additional data so that I can get a force deflection curve later on. Okay, so let's actually do the model check. Okay, that was okay. Let's do a simulation checks. This will also be okay, unless I missed something along the way, which I don't think I have. Okay. Ordinarily, when I do this thing once, unless I make some dramatic changes to my tree, I will not do these first two steps, first two stages. I'll just go ahead and run it. Okay, done. Okay, and now we're going to run it. There we are. And you'll see that it will go, at some point it will stop. It says error detected or failed due to error, stuff like that. We'll see. Which means the load control is not going to work in this problem. Even if I had a spring, if the stiffness of that spring was very low, it's essentially there is no spring. We can think about it as no spring, and it will stop. Okay, so we're gonna look at the stuff up here. At some point, it says terminated or stopped due to error, etc. We'll see. Right here. See, analysis failed due to errors. And then you can go and check what kind of error. I knew this was going to happen, so I just wanted to show you that it is true. Okay, so now what we're going to do is we're going to go here to structures, under load. I'm going to delete this force. Right click, delete. Okay, so we're going to go to loads, and there is a translation here, specifying translation. See that? Apply translation. You select it, you select this point, okay? And in the Z direction, we're going to put a 55 millimeter, negative 55 millimeter translation, okay? Now, I want to remind you that uh, when a downward load of 13.2 is applied, it should give you 55 millimeter downward displacement, okay? So I don't know this load, I deleted it, but I did put 55 millimeter downward displacement. So we're doing it, solving the problem as displacement control, okay? All right, so everything is okay. You can see that this is the icon for downward displacement. All right, now what we can do, there's two things we can do. First of all, we can run this thing and see whether it works or not. And I'm sure it's going to work. And then we come back and ask for additional data and run it again. Okay, so just to be on the safe side, let's run this thing, make sure it will work, except that it will give me the 13.2, in the last step, it will give me 13.2 Newton downward force. However, I cannot plot the load displacement curve because I need to ask for extra data. We'll see. So we're not specifying the force here. We're specifying the magnitude of the displacement, downward displacement, and force is going to come out in the wash. And it should be 13.2 unless those formulas are wrong. And I don't think they are. See? Extracting results did work. And in the final step, final increment, the force should be, the displacement should be, of course, the displacement should be 55 displacement. You can see that. If you go all the way to the last step, it should be 55 right there. Except that I don't have direct information about the force here. I can plot the stress, but that's really not what I want. Okay, so yeah, that's the value of the stress, but that's not what I want. So we know it worked. There was no issue. So we go back to scenario and ask for that extra data that we want. So we go here. This is where you ask for output, any additional output that you want. You click on it, and you're going to say, I want two things. I want displacement, and I want force. Now here, you can ask for RT. This one, see that CF? Before, in the previous video, I did CF, concentrated force, because I applied the concentrated force. It's not going to help me here. It's what I want is the reaction at the displacement that I specified, so RT deflection force. Now, at every step for the entire model, and the entire model here is, of course, basically 2 points. This one doesn't go anywhere. This one is good. It's okay, but in cases where you have a lot of nodes here, then doing it for the entire model is a bad idea, and we're going to have it at every increment, okay? And this is field data, okay? Not history. Good. So now we're going to run it again. We ask for the data that we want. I'm going to run this. Now, uh, I will have to massage my data so that I get exactly the same kind of force displacement curve that I showed you on the PowerPoint, okay? And we'll see that. See that. So it didn't stop. It actually went all the way through. There are some warnings here. It's a good idea to check these things. Now, if you go to the last step, uh, right, so what happens here, if you go to the displacement, you can get the value of displacement at different increments. The last one is 55. We close this, we close that. Okay, and let me actually get rid of this displacement, just show the undeformed model here. Okay, good. All right, so we go to plots, this icon, XY plot from field, XY plot from field. Please watch the videos on how to generate force displacement curve, and then the video which precedes this with the spring. I'm going through this process in more detail. There is a video segment called generating force displacement curve, and it slowly does these things for you. But anyway, you go to XY plot from field. Okay, so let's see now. We want displacement translation. See that translation? In the downward direction. Of course, there's only downward direction here, okay, even if I left the magnitude, because displacement direction x and y are 0, so it really doesn't matter. But yeah, so just leave it like that. And if I say apply, oh, the support is this point. It says, where do you want to do this? Obviously, I want this point. This is the end, right? There's only two nodes here, this one and the other one on the left side. So that's what I want, and I say apply. So notice that what happens is that as the dummy time goes from 0 to 1, the displacement goes from 0 to 55 millimeter. Okay, good. Now, let's change this thing. Let's change this thing to RT, reaction force. Okay, it did. And I don't have to select the point, it's the same point. If I, and the magnitude, I don't want the magnitude, I want the downward displacement. So the vector component 3, okay? And apply. There. Okay, now this is fine, force versus this deflection. By the way, notice that at the end of time 1, the magnitude of the force is negative roughly 13.2. But this is not how I want my plot to be plotted, okay? I want it to be kind of upward, okay? In other words, see, I put a minus there. So I want generate exactly this thing. That's what I meant by massaging this data. So here's the situation. We go back there, we close this, and we close that, and we go to XY plot from expression. The first one, remember, is the translation. The second one is the force, downward force, okay? So I go to f of x. What I like to do, I like to take this force, see that? This force, I want to multiply it by -1. So I say times, select this, times -1, -1, apply. Notice that it flipped it, okay? So good. Now, uh, what I need is go to combine. This one I don't need anymore. Let me get rid of it. Actually, we can get rid of it here. Okay, good. So we go to combine. I want the displacement, the first curve, and the one that I multiplied by -1 to be plotted against each other. apply, and there we are. This is exactly that curve, okay? And let's just check our values here. If I go to my, what is that, the trig, this is cursor, okay? And if I move this, and I go all the way to 55 millimeter, notice that the value is roughly 13. On the very top, you can see that it's roughly 13, uh, roughly 13, okay? That's because this is not quite at 55. But anyway, so we generated our force displacement curve. The moral of the story is that uh, when we did this thing as force control, it did not converge. When we did it as a displacement control, it went all the way, traversed all the curve, the entire curve, including the place where instability occurs, and we duplicated whatever his theory is predicting. Now, in a future video, I will go back and do it a with a force control, except that I will have to use the static Ricks step. Otherwise, it would not work. All right.